Hello. This time, as the third content. In Chapter 6 Timer Counter, I will explain the output mode of the 8-bit timer counter. As you can see, timer counter consists of 6 chapter and exercises. This video explains the output mode of the 8-bit timer counter. Let's take a look at the output modes of the 8-bit timer counter. The output mode can be confirmed in the interface like this. There are 4 modes: normal, phase correct, PWM, CTC, and fast PWM. First, let's look at normal mode. Normal mode is the simplest operating mode of timer counter 0. This will be a mode in which only upcount operation is performed and clear operation does not exist. Additionally, at the moment, the TCNT 0 value 0xFF to 0x00 to the overflow interrupt flag of timer counter 0 becomes 1 and an interrupt occurs. A value other than 0 can be used as the initial value of TCNT 0. In this case, we assign the same initial TCNT 0 value to the place where the overflow interrupt occurred. In this case, it can be used to create the same period. This can have the effect of making the period for interrupts the same and becoming constant. For example, when in timer counter 0 of ATmega128 16 MHz is 0x02, it is divided by 8. If the TCNT 0 value is 56, it is 38 in hexadecimal. When the timer interrupt mask is set to 0x01, the value counted until overflow occurs is 200, which is 256 minus 56. So, if you calculate the period, 1 divided by 16 microseconds times 8 times 256 minus 56 will be the final period of 100 microseconds. You can see the development process of the calculation formula that results in this 100 microseconds, as I have marked it separately at the bottom here. Therefore, we need to set the value of TCNT 0 to 56 whenever an overflow interrupt occurs. In this case, the interrupt will continuously occur every 100 microseconds. So, we somehow keep the TCNT 0 value as 0x38 in hexadecimal within the interrupt timer 0 overflow service function. The result is reflected as a decimal value of 56, so an interrupt can be called at regular periods. So, you must not omit this information. Then, I will explain in more detail the formula by which 100 microseconds is calculated and then move on. 1 divided by 16 million times 8 times 256 minus 56. First, if you divide 1 by 16 million, you get 0.7 zeros, which is 625. 0 point contains 7 zeros, and 625 multiply 8. There are 0 point contains 6 zeros, and 5. 0 point contains 6 zeros and 5. Multiply 200, you get 0.0001 second. 0.0001 second is 0.1 millisecond. So if we look at the units, we finally see that it's 100 microseconds. This equation will be calculated as if you enter it into a scientific calculator. This concludes the explanation of normal mode. This time, it will be the second content in 8-bit timer counter. Output mode. Let's take a look at CTC mode. In CTC mode, clear and set operations occur when the register value of TCNT0 increases and matches the value of OCR0. The result is output as a waveform externally. The value of OCR0 is cleared to 0 at the very next clock. And then the value of TCNT0 can be from 0 to 255. OCR0 can have the count value of the top value as the maximum value. Look at the diagram below. When the TCNT0 value increases and matches the OCR0 value, a set occurs. Clearing occurs when a match occurs with the second OCR0 value. In this way, two comparison matches must occur to create one PWM waveform. So, as you can see here, one PWM waveform 2 is included when calculating the frequency. Next, when a comparison match interrupt occurs, the OCF0 flag becomes 1. When does this case occur? When the counter value TCNT0 matches OCR0. The TCNT0 value immediately becomes 0. And at the moment the next clock is encountered, OCF0 becomes set and an interruption occurs. So if you go here like this, you can see the interrupt comparison match service. Like this, you will be calling these services. The next important thing is when the value of TCNT0 is compared with the value of OCR0. If the OCR0 value is suddenly set lower than the TCNT0 value, the counter value will increase to the maximum value of 0xFF. And then it changes to 0. We call the situation where CTC behavior like this occurs a glitch phenomenon. So, we need to control it to prevent glitches from occurring. In CTC mode, waveforms can be generated through the OC0 pin, and when the toggle mode is set, as you can see, when the toggle mode is set like this, a square wave is output. The formula for calculating the frequency for output is as follows. We usually need to know the OCR value to generate a specific frequency. Therefore, we need to convert this equation to OCR0 equation. So, this converted formula is implemented in the Excel file I will provide. You can use this file to calculate the OCR value for a specific frequency. Of course, in order to output OCR0, we need to set bit 4 of PRTB to output the data input-output settings. So, up to this point, we have looked at CTC mode. This time, we will look at fast PWM mode. This mode is very useful for creating high-frequency PWM waveforms. The counter repeats the increase from the bottom of 0 to the maximum of 0xFF. So, you should know that the counting operation continues from 0. In non-inverting output mode, the value of TCNT 0 is continuously compared with the OCR 0 register. And if a match occurs, a value of 0 is output through the OC 0 pin. If the TCNT 0 value becomes 0, it will be in a mode where 1 is output. As you can see here, clearing occurs when the TCNT 0 value increases and matches the OCR 0 value. It creates a square waveform that goes up to the top value and becomes a set. However, if you use reverse mode, this is the opposite of set and clear. And where a comparison match occurs, it becomes 1. And it is cleared where the top value is met. The formula for calculating the frequency of the waveform output through the OC0 pin is as follows. 256 is entered. Of course, to output OC0, you must set the data direction to output pin 4 of PRTB. When does the overflow interrupt of timer counter 0 occur? Occurs at the moment the value of TCNT 0 changes from 0xFF to 0x00, and then an output comparison interrupt occurs. At the moment, the value of TCNT 0 matches OCR 0. So, as you can see, if you look for these two interrupts like this, please know that an interrupt can occur. Well, up to this point, we have looked at fast PWM mode. This time, we will look at the fourth content, phase correct PWM mode. This mode is useful for generating PWM waveforms with high resolution. The TCNT 0 value increases from 0 to 255, and then decreases to 0 again. So as you can see, increasing and decreasing occur. So we can use the term dual slope when compared to the normal comparison output mode. If the value of TCNT 0 matches OCR 0 during upcounting, a value of 0 is output through OCR 0. If TCNT 0 value matches the OCR 0 value during downcounting, 1 is output. As you can see, when counting down, it becomes set, and when counting up, it becomes clear. We can check that the high-low ratio in the output PWM waveform changes depending on the value set in OCR 0. As you can see, please be aware that the size of the high ratio changes depending on whether the value of OCR 0 goes up or down. You just need to know that the high ratio changes in one frequency waveform. So what results can we get from PC PWM mode? Adjusting the compare match value. If the comparison match value is lowered, the period becomes shorter and the duty ratio decreases. If the value of OCR 0 increases, the period becomes longer and the duty ratio increases. Well, I've explained it up to this point, and I'll explain it again. We will explain phase correct PWM continuously. In this mode, the frequency of the waveform output through the OC0 pin is determined by the following formula. 510 is included here. 510 is 255 times 2. To get 510, this is because up counting and down counting are performed. The frequency of phase correct PWM mode is reduced by half compared to fast PWM mode because there is up counting and down counting. In order to export the output waveform to the OC0 pin, you must set the data input-output direction of pin 4 of PORTB to output. In this mode, an overflow interrupt of timer counter 0 occurs. When does it occur? Occurs when the value of TCNT 0 reaches bottom. Then, output comparison match interrupt also occurs when the value of TCNT 0 and OCR 0 match. As a special case, extreme values can be given to the value of OCR 0. If a value of 0x00 is given to OCR 0, logic 0 is continuously output to the OC0 pin. If you give a value of 0xFF to the value of OCR 0, a value of 1 can be continuously output to the OC0 pin. If output is performed in inverted PWM mode, the opposite logic value described above will be output. This concludes the explanation of phase correct PWM. This time we will look at the timing diagram of timer counter 0. This is the case where the prescaler is 1 and 8. First, in the case where the prescaler is 1, as you can see, when the system clock comes in by 1 clock, the TCNT 0 value increases by 1, reaches the max value, and then changes to bottom. The moment it changes to bottom, we get a phenomenon where the timer overflow 0 interrupt becomes 1. This phenomenon can be achieved except in phase correct PWM mode. In a situation where the prescaler is 8, as you can see here, only when 8 system clocks come in does 1 TCNT 0 value increase and reach the max. It will change to bottom. So, the moment it changes to bottom, a timer overflow interrupt occurs. As you understand, the higher the prescaler, the longer the period. Please Note that when the prescaler is lowered, the period becomes shorter. So far, we have looked at the timing diagram of timer counter 0. Let's take a look at the timing of changes in the output compare flag 0. It can be divided into CTC mode and non-CTC mode cases. If it is not in CTC mode, the TCNT 0 value increases up to the OCR value and does not fall to the bottom, but continues to increase the OCR 0 value by 1. So, as you can see, even if it matches the OCR value, the TCNT 0 value continues to increase. On the other hand, in CTC operation mode, it falls to the bottom. As you can see, it goes to the top, then drops to the bottom. And at the moment it changes from top to bottom, OCF 0 becomes 1. So by dividing it into these two, we can understand the timing of changes in the comparison match flag. This time, we will look at the output comparison unit of timer counter 0. The device diagram is as follows. Looking at the main output principle, output can be generated by continuously comparing TCNT 0 and OCR 0. So, they are continuously compared. And if a match occurs between TCNT 0 and OCR 0, the flag bit of OCF 0 is set and an interrupt is requested immediately at the next clock. OCF 0 is automatically cleared. This is the case when interrupt processing is performed. However, if we use software, we can clear it by directly writing 0 to the corresponding bit. If the value of TCNT 0 and OCR 0 match, a waveform can be generated and output. It is output through the OC0 pin. The output form of this output waveform at this time is determined by the various output modes we explained previously. You should know that the bit is output according to the WGM 0100 and COM 0100 bit settings. All right. So far, we have looked at the timer counter 8-bit output mode.